Hello everyone. My name is Dongdong. I'm a software engineer from Canonical. So today my topic is going to be using eBPF to developing a powerful tool for diagnosing Ceph performance issues. So before I start, may I ask a question? How many of you have used eBPF before? If you could please raise your hand. Okay, not too many. So I believe this we are going to be very interesting. So this is my agenda. First, I'm going to describe a life cycle of OSD operation that's happening inside an OSD. Then I'm going to talk a little bit about the current performance analysis methods and the limitation of it. Then next, I'm going to introduce the UProp and eBPF technology that I've been using to developing a great, powerful performance analysis tool. And last, I'm going to demonstrate this tool. So this is a picture of the OSD write operation life cycle. So as we can see, there are mainly can be divided into three levels. The first is the messenger level. And at the first stage of the messenger layer, an OSD will start to receive the first byte of the write operation. At the second stage is when the OSD fully received the write operation. So the latency between these two stages are mostly decided by the networking performance or the write operation that you are trying to send to the OSD. So once the operation has been fully received by the OSD, it will be dispatched to OSD level. At the first stage of the OSD level, the operation will be put into a OSD OP sharded queue, and it's sitting there and waiting for the OSD OP thread to pick it up and process it, which is the second stage of the OSD level. So once the OSD has processed this request and considering that this request is good to move forward, it will be dispatched to replicated to the sub-OSDs, and in the same time, it will be submitted to the local storage, which is Blue Store. Now we come to the last level of the life cycle, which is the Blue Store layer. So at the first stage of the Blue Store layer, it will allocate disk space for the data that you are trying to submit. The next stage of the Blue Store is submit the data to the main device. And the last stage of the Blue Store layer is to submit the metadata to LogsDB. So the LogsDB might sit on top of the main device, same with the data. And it can also sit on top of a separate DB device. So it's depending on how you configure your OSD. So once the sub-OSDs has replied to the primary OSD and the Blue Store, the local Blue Store has applied the write operation, the primary OSD will reply to the client. So this is a whole life cycle of a write operation that's happening inside an OSD. So the point to understanding the detailed latency of a write operations life cycle is help us to quickly identify where the bottleneck is if you are hitting some performance issues. For example, if you are seeing slow request. So two examples. So if you are seeing the large latency that's happening at the first two stages of the messenger layer, it's probably indicating that you are having a networking performance issues. And another example, if you are seeing the OSD operation has been sitting in the queue for a very long time, that might be an indication that your OSD is very busy. And you probably need to increase the queue or the thread, OP thread number. So how can we do that in order to understanding the detailed latency? of the life cycle. So with the current methods, we have some way, but let's identify whether they can work. The first is the perf counters. So Ceph does really provide very detailed performance latencies at different level. But the downside is that the latencies are all aggregated. So which means the outliers can be easily masked. And there is no per IO latency there. So it's hard to see the bottleneck of a slow request. And also there is no latency distributions regarding to different IO sites. So for example, if you are having two IO, one is 4K, another is 4 megabytes. So the average of these two IO's latency is not really very meaningful. Another way is to enabling the debug logs. So if you are enabling a really high verbose debug log like debug OSD 20 and debug Blue Store 20, it is true that you will be able to build the life cycle latency of any operation. But the downside is that the disk space will be filling up very quickly. Gigabytes log files could be generated in less than 1 minute. And it often results millions lines of logs, and it's difficult to trace a single operation just by human eyes. And so that's not really very ideal. And the third way is you can use some admin circuit command like dump OPs in flight and dump OPs historic slow OPs. So they're great. They can allow you to see the latency, the life cycle latencies at messenger level and at the OSD level, but it lacks the Blue Store level latencies. So, and also the output is not really easy to consume. It often requires significant time to do the post-processing in order to get a good insight. So the last way that is maybe there are other ways, but I just listed 4. The last one is LTTNG and block-in. So those are static tracing. So which means you have to insert the code into Ceph and rebuild it in order to get the info that you wanted. And also the overhead. So I believe the overhead is very low, but that does always exist even you are not trying to debugging. And I think it seems not included in the default building. So it's not really easy to use in production. So how to overcome those limitations and get the detailed life cycle latency? I've been looking around. I think the eBPF and uProp is great kernel technology that could allow us to fulfill that request. So let's look, what is uProp? uProp is a mechanism that's offered by kernel, allowing you to trace user space code. And those trace points can be added dynamically on any user space addresses. I pasted some code here. They are the core interface for that a uProp provided to a uProp user. The first is the uProp register. So this function helps you to register a uProp to the target binary that you wanted to trace. Let's look at the 3 parameters. The first one, inode. Inode is obviously pointing to the binary that you are trying to trace in. The second one, offset. This actually represents the instruction address that you wanted to inject the uProp to. The third one, uProp consumer. As I also pasted the code of uProp consumer below. As we can see, this structure has defined some function pointer. The most important one is the first one, handler. I will call it uProp handler. So in this function, you will define, so this is a user-defined function. So you need to implement the code in this function in order to read those user space memories that you are interested. Mostly those are variable or the parameter values that you are interested. So as we can see, it's not difficult to interact with uplop. You only need to specify 3 items. The first is the binary path that you wanted to trace. Second is the instruction address, where you wanted to inject your uplop to. Third is that you need to implement a uplop handler, which defines what you wanted to do with this uplop. So this. And next, I'm going to introduce how uplop works. So looking at the left side of the picture, we have the original instruction set of a user space program. The next, we decide to inject a uplop to instruction 3. And after the injection, we can see the instruction 3 has been replaced to a breakpoint instruction, which is in 3 in my CPU architecture. So once this application has hitting this instruction, this breakpoint instruction, a trap will occur. The kernel space will take over. In the kernel, it will first save the user space context and then execute the plop handler that you defined. And after that, it restores the user space context. Then it will execute the original instruction 3, which you just replaced. Finally, it will jump back to the user space and starting the execution from instruction 4. So this is how uplop works. Next, I'm going to give you a simple C example, very simple example. So I implemented a C file. It just included 2 functions, main and func. Next, I compiled it with GCC. Then I attach it to GDB. And I use the disassembling func command to see the original instruction of the func function. And please pay attention to the first instruction, because next I'm going to use the ftrace command to register the uplop to the entry of this function. And we can see after the uplop is registered, we can see the first instruction has been replaced to int3, and original one was NBR64. So after this, your uplop is registered. You just need to wait for the program to hit that int3 instruction. So how to use uplop? The most 2 popular ways are ftrace and perf plop. As we can see, the ftrace and the perf plop all provide very easy way to use them. They provide single line command way for you to consume the uplop. Take a look at the ftrace way. This example is I wanted to trace the OSD enqueue function and print out the parameter that I'm interested. So I only need to pass the binary of the Ceph OSD and then the entry address of the enqueue function. Next, I just need to pass the memory address of those parameters that I'm interested. So as we can see, the benefit of using ftrace and perfplop is that they hide all the technical details that you need to know in order to interact with uplop. But the downside is that they can only act as a dynamic print-k-like feature. You can't implement complex logic. So that's because it's unable to provide programmable way for you to implement a powerful tool. So next, I also looked at uplop in a kernel mode way. So as we can see, it indeed provides a programmable way for you to do dynamic tracing. You need to define the uplop handler. But the downside is that it requires you to build and insert the extra kernel module, which might always bring some overhead. Oh, sorry. So next is the eBPF. I looked at eBPF, and I think it's a great kernel technology that I can use to implement a powerful tool with uplop. So eBPF is a kernel technology since 4.4. It provides an easy way for developers to add their own programs into the kernel without the need to changing the kernel code or loading extra kernel modules. It also provides eBPF maps to pass data between user and the kernel space. And also, it's able to verify the safety of the program and prevent it from damaging the system. This picture is an overview of how eBPF works. It's very easy. You first just need to define a C source code. This is a BPF program code. You need to implement it in C. It will be running inside the kernel. What this file does is that you need to implement those uplop handlers that you wanted to do with your uplop. And after that, you pass this file to LLVM, and then it will generate the BPF program bytecode. And another thing that you need to do is implement a user space program. This will run in user space, and you can implement it with C, C++, Python, or Go. And as long as the language has the capability to deal with BPF system call, in this user space program, you actually only need to do two things. First is to use the BPF system call to load the previous compiled BPF program into the kernel. And once the kernel has verified that the BPF program is OK and it won't damage the system, the user space program will call another BPF system call and try to attach this BPF program to the target instruction address. And then it's done. And one of the things that makes eBPF so powerful is the eBPF maps. It allows the user program to interact with the kernel space. You can easily pass data in or fetch data out from the kernel. So this is an overview of eBPF. Next, I'm going to give a code example that how I implement my tool. So, for example, if I wanted to write an eBPF-based program and instrument to the function entry of OSD DQOP and read the OSD OP's client ID and request ID, note that the client ID and the request ID can all be obtained from the parameter OP. It's just you need to dereference it multiple levels in order to get the target value. So how I do that? It's very easy. I just need to first implement an eBPF program. And this is going to run inside the kernel space. And in this program, I need to define the uplop handler. Here is uplop DQOP. And this function takes a parameter ptrex structure. This structure contains all the user space register value, which means you are able to access any local variable or global variable or parameters that you need to trace. So first statement, I get the parameter OP's value from the RDX register. Next, I need to use some BPF probe read user function. This function is help you to read user space memory. And what you need to is just you need to provide the user space, exact user space address to this function. And after that, I just pass this program to the LLVM, and LLVM will compile this and to the bytecode, which will be loaded to the kernel later. Another thing I need to implement is a user program, which will be running in the user space. As we can see, it's very simple. There are two statements here. The first statement is it will load the above compiled BPF bytecode into kernel. The second statement will just attach the bytecode to a specific uprob event, which will be triggered when executing the instruction at the offset, the specified offset. But we can see in here, I used all the hard-coded parameter offset and the function address. So, which means this will be version dependent. If you just upgrade your OSD, those values will be invalid. So how to make it version independent? So I'm looking around. eBPF is not able to do this. It's because eBPF is not user space symbol awareness. So finally, I found the answer is that we have to pass the debug symbol, which is the DWARF info. So I have implemented the DWARF parser in order to get those functions and variable addresses. Next, I'm going to show a basic idea like how to pass the DWARF. First, I download the debug symbol, and then you can run the obj dump -wi, and you can see all the DWARF elements. I've given 3 examples here. The first is the DWARF tag subprogram, which actually represents a function. The most interesting attribute is the DWARF attribute low PC. The value of this attribute is the entry address of this function. And the next DWARF is DWARF tag formal parameter. This represents a function parameter. And the interesting attribute is DWARF attribute location. So the value of this attribute specifies the address of this formal parameter. As we can see here, the parameter's address is -24 from the frame-based register. The third one is the DWARF tag member. This represents a class or a structure member. As we can see, the last attribute, the data member location, and the value of this attribute represents the offset of this struct or class member. Sorry. So finally, I implemented the DWARF parser, and now I only need to specify the plopped function name and variable name that I'm interested. I no longer need to hard-code those address. So my DWARF parser will figure out the corresponding memory address for those functions and variables, and then pass those user space addresses to the eBPF program through eBPF maps. So I think that's next is demo time. I'm going to demo the OSD trace, this tool that I implemented. Okay. How to do that? It's not working? Okay. Sorry about that. Only 10 minutes. 10 minutes is demo.
You may have to hit it multiple times. Let's see. So function. Oh, here we go. So you want mirror, and then just let it. There you go.
Okay.
Yeah.
So I've got a small Ceph cluster. Sorry. On this node, I have 3 OSD. So I'm going to run the OSD trace tool on this node. now it's starting to pass the DWARF info. So it's take a little bit time. Sorry, the performance is not so good. I just implemented this few days ago, so still haven't got the time to improve it. So now those uprobes has been registered and attached. It's waiting there. It's waiting for I to feed some workload so that it can start to print out those life cycle latencies of the operation. Next, I'm going to, in this node, I'm going to generate some workload. Let's see. And then I go back to this. As we can see, it's starting to generate the output. So it's an IO-stat-like output. The difference is that IO-stat will print out those latencies from kernel and driver level. And my tool is going to print the latencies of the OSD process level. Those latency units are microseconds, and I'm going to introduce from each column. The leftmost one is the OSD ID. Next is the read per second, because I haven't implemented read yet, so it's all 0. The next is write per second for each OSD. Next, read is not implemented. Then next is write KB per second. This is the throughput of the OSD. And then next are the lifecycle latencies. The first one is the receive latency, which is the messenger level at the first 2 stage. It measures the time that how much time the OSD spent to receiving a write operation. The next is the dispatch latency. This is the latency measures the time that the OSD spent to dispatch this message from messenger level to OSD level. Next is the queue latency, which is the time that the OSD spent waiting in the queue. Then next is the OSD latency. This is the time that OSD spent to process this, to verify this operation after it got dequeued and before it submit to the BlueStore. Next is the BlueStore allocation latency. This is the latency that BlueStore spent to allocate the disk space for the data that we are going to write. Then next is the BlueStore data latency. This is the latency that measures the time that BlueStore used to submit the data to the main device. The next one is the BlueStore KV latency. This is the latency that BlueStore spent to submit the metadata to LogsDB. And the final one is the operation latency. This is the total latency that the OSD operation has stayed in this OSD. So these are all the latencies. Next, I'm going to give 2 examples to see how this tool can be used to diagnosing real performance issues. So this is still generating. For example, I wanted to inject some packet loss on this node, on the network card. So I'm going to open another terminal. Before that, let's take a look at the current receive latency. It's around 400 microseconds, right? Around 400 microseconds. Then if I inject the data loss to 25%, then let's look at the receive latency now. You see, sometimes it's going to report even 8 milliseconds or even beyond 10 milliseconds, 15 milliseconds. that's easy to observe, right? So next I'm going to fix the packet loss, and then let's see if it's getting better. Okay, we can see the receive latency is better. This has correctly reflect the network side receive latency on the messenger level. Next, another example I'm going to show you is to give it some 4K unaligned workload. Before that, I want you to take a look at the BS allocation latency column. BS allocation latency. It's now just around like 100 microseconds, right? Then if I give it some 3K, it's 4K unaligned. Then let's see. It increased a lot, right? It increased from 100 microseconds to several milliseconds. So why is that? It's because when BlueStore receives the 4K unaligned write, it will need to trigger 1 or 2 extra read in order to make it 4K. So this happens in the BlueStore allocation phase. So as you can see, it captured this behavior. So this is all my demo. Some future work. So because I just implemented this tool, I know there is a long way to improve it. For example, I need to detect the OSD background task because those background tasks can have significant impact to the OSD operation, to the performance of the operation. Like if there is a PG deletion that is happening on the OSD, if there is a deep scrubbing, if there is a locksDB compaction, if they are happening, I should print it out to indicate that the OSD is currently having this kind of background task so that I can expect a bit latency of the operation. Another thing we can do, because it can trace OSD, it can trace any other Ceph demo, including MDS, monitor, RGW, Ceph client. So that's all my talk. Thank you. Any questions? How to do that? Sorry, what the issue? Ah, okay. So is there any question? Which latency? PSKV?
Well, you had a KV, I forget what we called it, but then also the data write latency on the log place. Those are both high in the demo that you just did. I was curious if you've ever gone back and looked. I'm guessing Ceph data.
Yeah, those normally are those bottleneck. Like you are submitting the data to the block device, then you are submitting the metadata to locksDB. The demo that I showed are all based on HDD. So, yeah, if it's NVMe, it's like 300 microseconds. By the way, the Ceph version that I just demoed is based on Quincy.
Okay, so you also had Gabby's allocation PR in there for making faster allocations, right?
You mean the PR of my tool?
For Quincy, I think it had it. Yeah.
Yeah.
Cool. That was all I had to ask.
So any other question?
How much of your work is open source, so I can grab it?
Yeah, I'm going to open source this. It's just I just finished the tool like a couple days ago. The code is still a mess. So after I organize the code, I will open source it. So yeah, if you are interested into the log, I can publish it as soon as possible.
I actually had a code-related question too. Have you had any weird issues with libdw? I'm trying to debug some code I've got with it that hasn't been working right.
Yeah, not really. Currently, it's working quite good for me.
It is? Okay. That's probably bugging my code then.
Yeah. Okay, thank you.
How well your OSD trace tool scales? Can you run that against 100 OSDs at the same time?
Sorry, I couldn't hear very clear.
Interesting tool. Can you run that against like 100 OSDs at the same time? What is the performance penalty?
You mean run it against multiple?
Yeah, you showed 3 OSDs.
Yes, yeah.
So what about 100 OSDs?
So this is a command that's currently running on a host. So if you are having 100 OSD on a node, I'm not sure. So the current cost is that when you register when you're using the uprob, right? The uprob is going to trigger a context switch between the user space and the kernel space. So this is the I think this is the only major cost. And it's only like use 1, 2, 3 microseconds. It's not, I don't think the cost is a big issue, but
Okay,
I have to
thank
find
you.
out.
Hey, so maybe to add to this questions, so if the overhead is not too big, can you imagine in the future to have this for active monitoring, having actually plotting this stuff all the time and putting it into, I don't know, some Grafana dashboard and observing the performance all the time, or do you think the overhead would be too big?
That's a good question. So as I explained, each uprob will take probably 1 microsecond. So it depends. If you just inject like 1 or 2 uprob, that's going to be okay. But if it's a lot, there might be impact. So currently I'm not suggesting it to be always on monitoring, but it would be very interesting if it can. So yeah, I still need to measure the latency, the exact cost of this tool. So.
Thank you.
Okay, any other question? Okay, thank you.